Alright, there we go. Welcome to CS202 video 13. Today's topic is one topic, but it is one very important topic, and that is recursion. We kind of barely started introducing for the last 5 minutes last time, and I showed you how to do Fibonacci sequence in iterative code, which means a code with a loop. But now we're going to try to explore that into doing that same problem using recursion. And so what is recursion? Well, the definition of recursion I said in the book was, what did I say? The process of solving a problem by reducing it to smaller versions of itself. I think a better definition of that problem is that recursion is just recursion. That's the definition of recursion. And if you ask me what is recursion, I tell you, well, it's recursion. And then if you ask me what that recursion is, I tell you it's just recursion. And so it's a never-ending self-definition per se. If that makes any sense. And if it doesn't, then welcome to the club of recursion. We will try, though, to make it sense. We have in this definition of recursion what is known as a recursive definition. Okay, that's a long class. I was thinking, yeah, well, actually maybe this was the one day that it's very CPE-ish, but I'd say that the other maybe 85% of the class, you don't really need CPE. But I mean, you need some Boolean algebra and you need some basic understanding of binary, but not too much CPE. But yeah, hey, there you go. You got a taste of what 219 is like. For those of you that are here that were not here earlier, I live streamed my 219 class on Twitch today. When I normally do it on WebEx, and the reason for that was because I thought it might be useful because of the topics that we were talking about, which was how floating point notation works and binary in general, just binary arithmetics, which are useful at all levels, I would say. So anyways, back to this recursive definition. So thinking back to the Fibonacci, what we said was that this is Fibonacci. So the series of Fibonacci is going to be, there's some initial numbers of Fibonacci that are given, and that is going to be the first and second number. And that is that the first number of Fibonacci is always going to be 0, and the second number is always going to be 1. Or if you don't include 1 as part of Fibonacci sequence, then you can say that the first two numbers are always 1s. Either way works, depending on if you included 0 or not. What is also the case is that the following numbers of Fibonacci, once we have the first two, are going to just be the result of the addition of the previous two. And that repeats itself, because the third number is the result of the addition of the previous two, and then the next number is the result of the previous addition. And so it builds along. So for example, the next number here would be the addition of the last two, which is 21 and 34. Which would be 55. So that would be the next number in the sequence. And then after that would be whatever the result of 34 plus 55 is. And so we implemented a solution to do that using a loop. We said, let's go ahead and loop this to get the nth number being the 10th number here. And then basically, the way we compute that is we have two variables to keep track of the previous two numbers, because we need those numbers to compute the next number, right? And then we sort of build our way up to the solution, okay? That is a little bit backwards than what the algorithm tells us, because the algorithm or the mathematics tell us in a way, because the mathematics say that the nth number of the sequence is computed by, if we write down the mathematics, you know, we can say that n is equal to n minus 1 plus n minus 2. And n minus 1 is actually representing the nth number minus 1. Okay, so maybe we can put a bigger f in front of all of these subscripts, because that's what they really are. So we're going to say that f of n, like this, is equal to fn minus 1 plus fn minus 2. And that is going to be the mathematical definition of Fibonacci, which is the nth Fibonacci number is a relation of the addition of the previous two. The first one that is before it, which is n minus 1. So if this is, for example, the 10th number of the Fibonacci, it's going to be the addition of the 10 minus 1, which is equal to the 9, the 9th number, plus the 8th number. And so that is a nice and elegant way of explaining how Fibonacci works. However, in addition to this, we do have two special cases, which we are going to be calling the base cases of this, which are f of 0 and f of 1, which is the 0, well, if it bothers you to say that this is the 0th number of the sequence, then you could call it the first number of the sequence and the second number. It doesn't really matter. But since we are CS people, we're going to say that the first number of the sequence is going to be 0 and the second one is 1, okay? But again, it doesn't really matter. But the point is that, we're going to say that that is this. Again, if you like the other method better, then I will say that it's 1 and 1, okay? So again, if you don't think of 0 as part of the sequence, or also if you don't like 0 as being part of the counting system, okay? And so those are what we consider our base cases. And so this right here, along with these, either of these, either this one or the other one, is all we need to define the Fibonacci sequence. It's not enough to just say this one, because we don't have a starting point per se. But as long as we put that plus our starting point, or end point if you want to consider it that way, because you're counting down in a way, then that's it. That's all we need. We can describe it using all these examples here and the English things. We can code it with a for loop, but that's different than this very nice and simple definition. And if I had given this to you before I even tell you how Fibonacci works, depending on your experience with math notation, you may or may not have understood what I was saying. And, you might have been like, what is this? I don't understand this at all. And so, there's a merit of explaining something like this, right? But there's a stronger sort of jump of trying to go, even if you kind of understand how Fibonacci works, trying to convert this into code that we can actually solve with loops is even trickier, because if you think about it, with the for loop, we're going from the beginning, so from like the 0 and first numbers, up until the number that we want, okay? However, the definition is actually backwards in a way. Or actually, we're backwards and the definition is correct. But in a way, the definition is counting from the end number, so the number we're trying to get, to the beginning, okay? And so there are very different ways of thinking it, The definition says we can find this number based on these two numbers. However, those two numbers can be computed based on the previous two numbers, which would be like this one and this one. And then this number is based on this one and this one, right? So the definition is working that way. However, the code that we wrote is actually working from the beginning of the code and up. So it's saying, okay, we know this and we know this. So now to compute this, we're just going to add these two together, and then that's going to get us that. And then to compute this one, we're going to take these two that we have and add them together. So we're going totally different ways, okay? But the reason that we're doing that is because otherwise, with what we currently know how to code things, we just don't have an easy way of doing this yet. But now recursion is going to come to the rescue for doing this, because, what does this kind of look like? Having f of n thing. It looks kind of like a function. And so what we can do is we can try writing a function that can solve this. Now, we could make this a function as we have it here. All we gotta do is basically throw in you know, a little int. Let's say it's valid returning function. Fib for Fibonacci, and then pass in a parameter, which is the number that we're trying to compute. So int n. And then instead of 10 here, you know, we could replace that with I is less than n, with n being the nth number that we're trying to solve. And that's pretty much it. At that point, based on what we did last time, we essentially have created a function that can solve Fibonacci, okay? And so that function is nice because we can just, whatever the n is here from this is basically translating to that, and it's still not doing it in relation to that. However, it's still quite a bit of code, and also it is tricky because we had to sort of flip the algorithm upside down, kind of compute how we're going to do this. Then we have to keep track of a previous variable and then update it and all these things. So it was a tricky process that we went through to actually solve this, okay? Especially if you've never seen it before. So what I propose to you now is another way of solving it. A better way of solving it. At least for coding it. Not necessarily for the way it gets solved in the computer, but for us coding it. And that is going to be the recursive approach. And I will go ahead and define recursion a little bit better in a second and all the parts of it. But first I want to just jump right into it. And so let's look at how this is done right here. We are saying that we can compute f of n as long as we know f of n minus 1 and f of n minus 2. And so I can go ahead and write another function that is called fib, as before. And it does also take a parameter n. But rather than writing that complicated for loop, why don't we just write the definition as it's here, which is saying f of n minus 1 plus fib of f of n minus 2. And that is going to return to us the number that we want. So then why don't we just go ahead and say return, and that's it. And that is actually looking very much like the definition that we had in math. And will it work? Well, almost. It'll almost work. Because here's the thing. You know, the nth Fibonacci number into our int fib function takes an n, which is the nth number we're trying to solve. So let's say we're trying to solve 10 again. And it's going to tell us the answer if we know the previous two numbers, which, you know, if we plug in n here, we're going to have a function call to fib9 plus whatever fib8 is, which is exactly what the it's exactly what we're trying to solve based on the math formula, right? Now, we don't know actually what fib9 and fib8 are, but, you know, that's okay. We're just writing the definition. And if we call the function with fib9, then we will know, because what is fib9? What is the answer to fib9? Well, the answer to fib9 is that it's based on fibs 8 and 7 added together. And then we can let the code call those functions on 8 and 7 to figure out the other cases, right? But there is one extra thing that we need to add here, because right now as we have it coded, we don't have what is known as a base case. We have what is known as a recursive case, which is this function call here, which calls the same function that you just created, but we don't have a way of stopping it. So what's going to end up happening is when we get to fib2, we know that fib2 is based on the answer of fib1 and fib0, right? However, those answers we actually do know because they're given to us in the formal definition of Fibonacci. We know that they're equal to 1 and 0, right? So 1 plus 0 would be the answer to that. However, we don't have that in our code. And so what's going to end up happening is it's actually going to compute fib1 as a relation of fib0 plus fib -1 actually, because we haven't stopped the function basically. And then fib 0 itself is actually going to be computed as a relation of fib -1 plus fib -2. So I think that you can start seeing how this could go wrong very quickly and very easily, right? Because it's just going to keep going forever right now. And that is not what Fibonacci works. Fibonacci stops at 0 or at 1, depending on how you're looking at it. And either case scenario, there is a stop, right? And so how do we stop it? Well, look at the function definition. You know, we have the answers to fibs 1 and 0, so we could just write it into our code here to have those definitions by checking whether the n that we're passing in, which is the nth number of the Fibonacci sequence, is equal to 1 or 0. And if it is, then we don't need to do the addition. We can just return the answer. So we can say something like, if n is equal to 1, then we go ahead and return 1, because that's what Fibonacci 1 is telling us actually. Furthermore, we can also do another if statement saying if n is equal to 0, which is the other scenario, then that is equal to just returning a 0. And that's it. If we do this, then we go ahead and stop. So that way, when we do get to this fib 1 and fib 0 here, it's no longer going to try and do that addition. It's not going to do that anymore. Instead, it's just going to return 1 or 0 because it's going to enter that if statement. And in any other case, when we have 2, 3, 4, or anything up to infinity, whatever, you know, practically fits in our system, it's going to go ahead and return as an addition of the previous two numbers. Obviously, there is no such thing as a negative Fibonacci sequence number. It's not part of the definition here, and therefore we don't have to worry about it because it's never going to be passed in, right? And that is okay because again, that is giving it. It's not even defined in the definition here. What happens if you go to a negative number? So you don't even have to put an error check for that because it's never going to happen. Okay, and that's it. Let's go ahead and see if this actually works when we try to implement it, you know. So let's go ahead and just try that. The VM should be up and running by now. Yeah, okay. There we go. So this was the iterative version of Fibonacci that we had tested before, and we did get 34 once we fixed the little typo that we had here. So I'm going to still keep this, but I'm going to go ahead and put it in a function. So up here, we're going to call this function iterative fib. The word iterative basically means loop. Oh, I totally messed up the tabbing of everything there. There we go. And then this will return Chester answer. And just to test that the function works, let's go ahead and try calling it iterative. Here, I want to put a underscore there. my dog is like moaning. It's just annoying because I guess I'm squishing her. What was number 10? And then maybe you can try it on 11, or we'll try it on 9. Or 9, because we have that 9th number computed. So let's go ahead and try it also on 9. Like that. And yeah, let's give this a shot. Just make sure that we didn't mess up converting into a function. Yeah, we messed it up. Where did, oh, I see why. This has to be changed to an n, right? It's no longer always running on 10. It's running on depending on what the parameter is. There we go. So that's good. So the next number should be 55, right? So if we call Fibonacci on 11, we should get a 55. So yeah, okay, so it's all good. So now let's go ahead and implement the other one. So int fib, this one will just say fib. It's going to be a recursive fib. It is saying if, so we're going to have to start with these, which are the special scenarios that are given to us in the math definition, which by the way happen to be called base cases, because that's kind of the end to the chain of recursive calls that we do. And I'll go ahead and write that formal definition in a minute here. So otherwise we have the other scenario, which is when we do the math, when we do add the result of the two function calls. We happen to call this the recursive case. And there we go. So let's go ahead and see if that actually works. So let's add another end line so we can split them. And then let's go ahead and just call the function. So let's go ahead and say cout fib on the same numbers. Let's try. But this time maybe we can try also one of the special cases, so like 1. And then let me just copy and paste this a few times. Come on. Why? Guys. There we go. Okay. So 9, 10, 11. One more. Let's do the other special case, which is 0. Okay? So, as you can see, it works the same way, although we happen to be off by 1. Yeah, we're off by 1. Yeah. So, it worked nicely with the 0 and the 1, but I can see here that, oh, no, we are off by 1. Something's up because, let me see. We have 0, 1, 2, 3, 4, 5. So 9 should give us 34. And 9 is giving us 34. So actually, we're off in this version here. This one's wrong by 1. We can fix that easily, though. See that? So the iterative one was actually wrong by 1. Now they match because the 9 Fibonacci value. Well, I see what's happening. Before we set it like, it depends on what you consider to be the 9th. Are you saying the 9th starting from 0 or starting from 1, right? Because like the way that we had it here, I did have starting from 0 as a 0, right? So then, 1 is not the first item of the Fibonacci sequence. 0 is the first item. So by that token, do we consider this 9 to be the 9th number of the sequence or to be the 9th of the sequence? Well, they're both the 9th of the sequence, but like, this is technically, if we're counting from 0, this is the 10th item of the sequence, okay? So that's why we're having the discrepancy. So last time we were just basically saying that. So both were correct. It's just different interpretations of this. However, we're going to say that the number that we're passing in is the index of that number in the list. So that means the index 9 is actually the 10th number, okay? So yeah, again, the difference between math and CS people, right? Math people start counting at 1, CS people start counting at 0. Oh, yes, we're better, right? Okay, so let's look at that because we just wrote our first ever recursive function. As you can see, this piece of code, and here, let me write it as a comment on top. The math definition of this, I can't do subscripts here, but what I can do is actually I can switch over to that one other thing that I have here, that one, and then I can pull it up here. Almost worked, almost. When I zoom out, it just does it here. Okay. I can just shrink it. Okay, there we go. So as we can see here, this is what the math person told us to basically do. And then of course in the past we had to like really think about it hard to come up with this for loop version, right? That took a lot of brain power unnecessarily, because if this is what the math person gives us, the stuff in the blue box, then it'd be nice if we could just very easily translate that into code in the computer. And that's exactly what we did in the second scenario, because as you can see here, we have our two base cases, which is on the bottom square, you know, so the one that is, let's put that on a slightly different tone, maybe darker blue. Looks more like a purple, but okay. So that blue purple there, that is our two base cases, 2 lines of code. You know, there's 2 lines in the math definition, there's 2 lines of code. That's very one-to-one relation right there. And finally, our main sort of function that we're trying to do, which is f of n is equal to f of n minus 1 plus f of n minus 2. And bam, that's exactly what we have. So 3 lines of code, 3 lines of the definition. You know, I guess technically our code is 5 because we have the curly bracket at the bottom and then the function definition at the top. But, you know, other than that, it's very nice. Okay? And it's giving us the answer. However, you know, you might look at this and like, if you're trying to solve this by hand, you might be like, oh wow, this is tricky because I gotta make like this chain of things. And I'll show you how to do that in a minute. But let's say all of a sudden that we wanted to make our own version of Fibonacci, which we're gonna call, I don't know, Twitch-Onacci, okay? Okay, so we're gonna make the Twitch-Onacci sequence. And the Twitch-Onacci sequence happens to be f of n is equal to f of n minus 3 plus f of n minus 5. Okay? And so this little Twitch-Onacci sequence, you know, we should have called it the Bob Ross sequence, actually. That would have been cooler. Let's call it the Bob Ross sequence. And then we can actually use an F here. Bob-Ro-Nachi sequence. I hope that's not like an insult or something. Yeah, okay. And so, this is basically telling us that the next number in the sequence is based off of the third previous number and the 5th previous number. We can even go ahead and add something even more here. So let's go ahead and do that. Let's add in also the 4th previous number. Like that. And the reason why is because if we don't do that, we're never gonna be able to really figure this. Actually, the sequence would have a lot of numbers in it, but they would have a lot of undefined numbers, which would be all of the even numbers. So by putting in an even number in there, we solve that. We could also potentially, to make this not so trivial, we could make that the 2nd. So I suppose in that case, just because it bothers me, I would want to put this one in front first. So yes, there we go. Wow, that's kind of cool that I could do that. And you can't see it though. Oh shoot, you can't see it. Let me shrink it. Oh, and then this happens to be a tree, a bench, and a shack in the woods. Okay, because that's what he likes to draw, right? Cool. All right, so we do need to have some base cases for this to work, because if we try to code it like that, you know, it's gonna go into like negative infinity basically and never stop. So the base cases are gonna be that you know, we're not going to use 1, because what did Bob Ross say about benches? You know, that he draws 2 benches because everybody needs a friend, right? So because of that, we are going to say that b of 0 is equal to 2. No 1s here. And then b1 is going to be another base case, because we need to have at least 3 base cases for this to really work. Is going to also be a 2. And then b2 is going to be I don't know, 4, just cause, you know, why not? And I think that is going to be just about enough to kind of get us going, I think. If we start out with something like 5, yeah, if we start out with 5, I think we'll be okay. Because if we start out with, I guess it still would be a good idea to, yeah, I think we need to have at least all the way to 5, to at least one more at least, okay? So we'll put b of 3 is going to be equal also to 2. And then I think now we have enough numbers for this to kind of work out, okay? Because if we try, and we're going to say that, you know, there's no negative numbers allowed, okay? And so now we're going to try to do b4. Okay, so 1 more so that b4 can work. So b4, we're going to make this one be another 4. Why not? And then b5 we can compute, because b5 is going to be based on 0, on potentially 2, and then on 3. So, yep, okay, yeah, so that's it. This is good. That's all we need. So now to write we have our function and we have our base cases. And so let's go ahead and say that we want to compute the, let's go easy. Let's just say we want to compute the 5th number of the sequence, okay? Using this. So the 5th number of the sequence, you know, maybe I'm gonna switch over really fast to the full tablet so that you can have space to write it. The 5th number of the sequence would be computed by plugging it into our function, because those are the only base cases that we have. Those were given and they were just picked random because I don't know, I felt like picking those numbers. I could have picked just about anything. In fact, I could have made one of those 100 if I wanted to. But anyways, so we're going to try to compute the 5th value using this function, which means that anywhere where we see an n, we're going to plug in a 5. So 5, 5, 5. And so now this becomes b of 5 is equal to b of 3 plus b of 2 plus b of 0. And we know exactly what that is, because this is a 2, this is a 4, and then this is a 2. So the 5th number of this, well, technically the 6th number, but index 5 of the sequence happens to be the addition of 2 plus 4 plus 2, which is 8, okay? And so just to test one more number up, we can go ahead and say b6. b6 would be the result of n minus, so let me copy it again. This is we literally just came up with this, so I didn't even like keep track of it. So that would be the result of b4 plus b3 plus b1, which we have here as 4 being 4, 3 being 2, and 1 being 2. And then this becomes 8. So that also happens to be 8. Interesting, but okay, cool. So, you know, if I was to try to code a for loop version of this, it would be kind of similar to the other one, but you know, still unnecessarily hard work. Where I can code this in how many lines? Well, I got a couple of these that are the same, so I could kind of put them all in one line. But essentially, if I wanted to have each variable be its own thing, or each if statement to be its own thing, then they would be in 2, 4, 6 lines, plus the 2 lines for like the function definition and the curly bracket at the end. So let's go ahead and do that. Okay, so we are gonna call the function, what is it, Bob Ross-Nachi, maybe it's like that, okay? Bob Ross-Nachi. And so Bob Ross-Nachi is going to take the parameter, and although, yeah, yes, call it N. I was gonna say call it B, but I don't want to confuse you guys. And so let's go ahead and write the recursive case at the end. And by the way, do you kind of see as to the why you want to do the if checks first before you do the function calls in the here? Does that make sense as to the why? And if not, it will eventually make sense. But let me just tell you for now. You want to check to make sure that you haven't reached the end before you go further, because if you do that, then you will never do the checks. I mean, it's kind of clear here because you see the keyword return, but sometimes it might not be as clear. But you always want to check what are known as the base cases before the recursive case. And I still have to go and write the definition of that. I'll do that after we code Bob Ross's sequence here. So let's go ahead and code it in. So it is going to be, it's actually kind of long, Bob Ross-Nachi, n minus 2 plus Bob Ross-Nachi n minus 3 plus Bob Ross-Nachi n minus 5. So that takes care of the function there, and then you see it up there. It's the same thing as that one. And then now we need the base cases. So the easy way of doing this without like having to have any sort of brain power involved to this, you know, because we're like tired or something, which, you know, it's a perfectly valid excuse, would be to just do this and say if n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and then you could go ahead and say 2, 4, 2, 4. However, you could also make this a little bit more efficient by combining the cases that give you all 2. Because I could say like if n is equal to 0 or n is equal to 1, return 2. Because both of them return 2 in the first place. And then I can also do that with n equals to 3. I can say if n is equal to 3, if n equal to 0 or n1 or n3, return 2. Because again, this one also returns 2. So I don't need that. And finally, I can also combine the 4s because they both return 4, right? So I can say n is equal to 2 or n is equal to 4, return 4. And so, you know, back to 5 lines of code only. So I actually didn't intend to do that, but my lack of creativity choosing numbers kind of helped to explain a point here. So yeah, so that worked out great. The only reason I actually picked even numbers was because I thought it would make the math easier. I never thought I actually would be useful for this. But hey, it's fate. So, I mean, it codes and it runs, but we actually need to call it. So let's go ahead and call our Bob Ross-Nachi sequence. First, let's call it on the 2 numbers that we already computed, because we know for sure that those will work fine. Are we going to hard code those formulas, or do we find them before we use them? If you want to find an area circle, you could do a pi radius. However, if Fibonacci sequence is an infinite number, how will you represent the summation of infinite sequence? Oh, well, this works as it is now for computing the nth number. And it will now, if you want to add all of the previous numbers of the sequence, because remember, Fibonacci is only adding the previous 2. So that's all you need. Now, if you're asking, can we write a function that can add all of the numbers before it? We could do that as well. That's also possible to do. However, as you said, it is an infinite sequence. So you can't just ask it to add infinite amounts of numbers, right? You have to ask it to add a specific amount of numbers. And that number has to be smaller than whatever we can hold in an integer. Or if you're using a float, then a float, right? But that we saw in the morning is not very accurate in general. So I hope that kind of answers what you're asking. But as it is now, yes, we are in the hard coding a formula because that's what the math is telling us to do, and that's okay. If anything, all the code that we do is hard coding in a way when we're writing formulas. We never write something, I mean, There are programming languages where you can write dynamic stuff, like you can write a function that is sort of created on the fly. You can do that in Python and stuff like that, but not in C++. So just to get a clear definition, a recursive function is a function that calls itself. Now you're getting it. Yes, exactly. Yeah, which is why in the beginning of the lecture I said recursion is recursion, because the definition to recursion is calling upon itself, which is look up, and actually I think in some dictionaries will actually do that sort of as a meme and put look up recursion. In fact, I think Google will do that. Yeah, Google has a little cool thing about that actually. Here, let me sidetrack into that mental break from this. There we go. If you go in here and go ahead and Google, well, first let's go to google.com, like actual google.com, and then let's type in recursion and see what happens. Did you mean recursion? Oh, thanks Google. Click. Did you mean recursion? Oh, okay. Click again. And you can see that it's trolling us. That's normally the autocorrect of recursion, like of typing something, because if we were to type like recursion with 2 C's or something, showing results recursion, search instead of recursion. Well, that's not a good. Let's type in a bunch of C's. Did you mean recursion? There we go. Thank you, Google. Okay, but now it'll still keep asking. See that? So yeah, Google trolls. Google smart people. So yeah. So as you can see, Google being CS people, they kind of get that good sense of humor from CS. So yep. So yes. Recursion, Google is calling upon itself. I hope you guys see now you get that joke. You can feel elevated understanding that joke. I don't know. All right, so okay, going back to Bob Ross's sequence here. Let's just go ahead and test it before we kind of define those terms. So C out Bob Ross, Nachi, and then we said we figured out that 5 would be 8, and then also 6 would be 8 as well. So let's start out by testing those 2 cases because we know for sure, because we worked them out by hand. So that did indeed give us 8 because it's right on the top, and then let's try 6, which should also give us an 8. I don't want to type more because it's already kind of too big, the code, so otherwise it'll go out of the page. So 8 also, and then just for the heck of it, let's try computing like the 15th number, just because I have no idea what this would be. Although I have a suspicion that it's going to be an even number because we don't have any odd numbers in the sequence because of the way we set things up with pluses. So I think that should give us an even number. Other than that, I have no idea what it is. I'm going to take a wild guess and say that it's going to be somewhere around 120. Okay? No, more. Probably like... No, probably 120. Alright, we'll see. 242. Okay, I was off by half, but not bad. Okay? Yeah. So, as you can see though, it was definitely an even number. So, there you go. Bob Ross now has a sequence of numbers. You guys go ahead and put that on the book next to Fibonacci. So, okay. Let's go ahead and switch over to the iPad to define. And by the way, if you want to work that out by hand, be my guest, and then let us know on the comments on YouTube if it actually worked out to be that right number, which I'm pretty sure it is because we're perfect coded all the time, right? So yeah, actually I don't think there's a bug in that one, so it should be accurate. So yeah, okay. Now let me open up the book here, and so I'm gonna give you a couple of definitions here. We have base case. We have recursive case. Doesn't say anywhere that, but this is the one that I personally know. And then we have recursive definition, I suppose. And I'm going to go ahead and say recursive function as well as a definition of my own sort of creation. Not that I created the term, but it's not in the book, I'm saying. Okay? In the book, they have like interesting things. They say general case. I'm not sure what they mean by that. They're saying equations 15-2 is general case. Okay, so they're calling the mathematical. And by the way, in the book they use factorial. I decided not to use that one because you can look at that one on your own time. You can also Google it. There's like billions of cases. There are actually billions of cases for Fibonacci as well. I think Fibonacci and factorial are the easiest examples when you're teaching somebody recursion. So typically somebody picks one or the other. But in the case of the book, they explain factorial. That's why I did Fibonacci. Okay? The one you won't find anywhere else is Bob Rosnacci. That one is authentic here, guys. So that one is pure to us. So yes. Okay. So they are calling general case the math formula, but I'm not going to put that because that sounds weird. So a recursive function is basically a function that calls itself. So we're going to put that in here. Function that calls itself. Or, and this is another rather interesting thing that can happen, calls a function that eventually calls a function B no, we don't need to define that. That eventually calls back on the initial function. So right now we have a function Fibonacci or a function Bob Rosnacci that is calling itself. However, there is another sort of scenario that could happen. You could have a situation where you have a function foo that calls a function bar, and that's all that happens in my code. And then you have a function bar that calls a function foo. Okay? And so now, if you call either of these functions, what's going to happen is it's just going to be like playing ping pong. It's going to be bouncing back and forth. So when I call foo the first time from like main or whatever, it's going to run this code and it's going to stop there and go to bar and then run that code, stop there, and then go to foo and then run that code and stop there. And so you can see it's just bouncing back and forth. This is also recursive. Even though you're not calling yourself, you're calling a function that eventually is going to call you back. So it's going to be also never ending unless we have a way of stopping it with a base case. This can happen to multiple tiers of like confusion, I guess, in the sense that like it could happen with multiple functions. So like you could have function 1 call function 2, 2 call 3, 3 call 4, and then 4 calls 1, and then you basically completed the circle until now everything is recursive. Now, why would you want to do this? Well, there might be a situation where it makes it easier to code that way, but more importantly, there might not be always a scenario where like 2 calls 3. That might be like in an if statement for a very special case, and it will still be a recursive thing because there is a special case, and as long as there's at least one case where you call yourself, we're going to be considering it a recursive function. So I guess that's something important to say. As long as in some special scenario the function calls itself, no matter if it's super weird and super rare, as long as there is that one scenario, we will consider that function to be recursive in nature. Okay? And so let me just go ahead and scoot this down here for now. So what is base case? Base case, first of all, a recursive function should always have, for it to be considered a recursive function, it should always have at least one base case and at least one recursive case. Okay? So one of each. Now, technically speaking, I could write a recursive function and never have a base case, and I would still consider it recursive, but at the same time, it'd also be useless to me. Because if you don't have a base case in a recursive function, what's going to happen is it's going to be the equivalent of me writing an infinite loop, in the sense that, like, it's going to run forever, but as we will find out in a little bit here, it's actually very, very bad. Because while I can actually have an infinite for loop actually run pretty much forever and not have any issues in my system, as long as I'm not like allocating memory or doing something bad, I could just have a little code that is just literally running forever, but no code inside, or maybe just a little print statement. And that is okay. I mean, it's bad, but there might be some purpose for that. And you can kind of get away with it. Although I highly would discourage you from doing something like that. You know, you kind of want to have a way of stopping it, at least maybe like a keyboard input or something. But you could do that. You could run them from the for loop. With recursion, yes, you could write something that recurses forever to kind of mimic an infinite for loop. However, the nature of recursion is going to mean that pretty soon you're going to run out of memory and your program system is going to crash. So that is why I'd say that it is necessary to have a base case for a real recursive function, because otherwise it's just pointless. Okay? And I'll tell you again more about that in a second, but let me first finish defining this. So what is going to be considered the base case? The base case is when the recursion stops, basically. Okay? It's a check to know when we are done. In the case of Fibonacci, it's going to be those basic numbers like f of 0 and f of 1. In the case of Bob Ross's Fibonacci sequence, that's going to be b of, I think, 0, 1, 2, 3, or 4. You can have as many base cases as you want. However, you have to have at least one base case in there. And this actually has to be useful, okay? It can't just be just like, oh, you know, that's why I had to really think about these base cases, because if I miss one of these, it might be possible that my series would never end, you know, with like when I ask it for 5, because 5, to compute 5, I require base case 0. And if I don't have that, then if I'm trying to call it on a sequence and there is no base case for that, it's going to assume that it's going to use that general formula here. And because of that, then it'll, at that point with 0, it's going to try to go with negative numbers and things will break down. So you have to make sure that your base cases actually stop all possible scenarios that you may deal with. And that's harder than it sounds. You got to really think about them to know ahead of time. It's like trying to predict all possible things that could go wrong on your first day of school. You know, that's a very hard thing to do, because until you actually run into a scenario that is bad, you might not have thought about that one. You might have thought about the easy examples, the easy cases, but there's always going to be one of those weird edge cases that you maybe didn't think about, and that's going to come back to bite you with the base cases. So that's just part of the debugging process. Recursive case, you have to have at least one, otherwise it's not a recursive function. So you need to have a way of, you know, a function, again, that's a call to yourself. Asterisk there, because again, it doesn't really have to be a call to just yourself. It could be a call to another function that eventually calls you back, as I was showing you with the chain of calls here. Okay, so little asterisk to that. So finally, we can say that a recursive definition is something that is again defined in terms of your smaller self, or more, or a better, that's the one the book says, but my better version of that is saying that is going to be something that is solved by calling yourself with a smaller, easier version of what you're trying to solve. So if you think back at 135, I said, or whoever taught it said to you, that one of the approaches to solving problems is to divide and conquer, right? Split a problem into smaller subsets of that. Recursion is one way of doing that. And yeah, that's pretty much it. It's not the only way of doing it, which is why I don't agree with the book of saying something that a definition in which something is defined in terms of smaller versions. But I guess the key part being saying of itself. Okay, so hopefully that makes a little bit of sense. Now let's talk a little bit about memory allocation and in general memory and how recursion plays with that and causes potential issues. Okay, so I think at some point in this class, I hope I did, but I don't know, at this point kind of 219 and 202 kind of melding together, I did talk about the stack and the heap in this class, I think, when we were talking about dynamic allocation. And so when you call a function in C++, you know, what happens is the operating system, your code tells the operating system, like, hey, I need to call a function of, let's say we're calling fib, okay? So let's say we are calling, we're calling fib8, okay? Fib8 requires fibs, no, let's do fib5, because otherwise we're gonna be here forever. So let's say we're calling Fibonacci 5, okay? Fibonacci 5 is basically the result of Fibonacci 4 and Fibonacci 3, okay? Now, these are going to be based, you know, so off other sort of subsets. So we got Fibonacci's 3 and Fibonacci's 2, okay? So I don't know what just happened. I think something happened, but I had no audio, I guess, inputting from Twitch. So yes, I will have to watch the replay later. Fibonacci 3 is based off of Fibonacci's 2 and Fibonacci 1, which this one we already know. So that stops at there. And finally, Fibonacci 2 is off Fibonacci's 1. And you guys are all like, I'm actually curious to see what just happened, but I'll have to wait until the end. But yeah, okay. So yeah, that's pretty much the chain. However, let me show you how this is actually kept in memory. Okay, so somewhere in memory, and for that I'm actually going to shrink it so that I can kind of put it to the side here. You can still read that probably like that. Okay, so in main memory, somewhere in main memory, in the stack side of things, you have your program gets loaded in by the operating system into main memory when you execute it, when you do ./a.out. And again, that's 219 land, but essentially you're putting in there your main code. And along with main, have your command line arguments and any local variables that you have. Okay, so now at some point in time, when you have a function call, you know, so for example, when you have a function call to fib5, because that's what you had in main. In main, you had something like cout, fib5, and line. Well, cout will have its own function calls, but let's just ignore that for now. Fib5 will have a function call, and what that's going to do is that's going to allocate some special space in the stack that we're going to call fib5. And then that will have its own local variables that the function requires and parameters as well. So it will have the 5 in there somewhere, like n equals 5, and so on. And then, you know, let's say for a second here, you know, I'm gonna let's just imagine, let's forget about recursion for a minute, just so I can make sure you understand this. Let's say fib5 calls on function bar, and that's all it did. There's no recursion, okay? Just bear with me for a second here, because I'm not to jump too far ahead here. In that case, we are gonna have another stack object here for bar, which will have its own objects. And then when this function finishes, because let's just say bar is just some function that like runs some code and finishes, then this gets removed from the stack, and you get back to fib. And let's say that fib at that point was done, then fib gets removed, and you go back to main. So when functions get called, it gets added, and when they finish, they basically get removed from the stack. Okay, and this is known as the call stack. And if you remember, I think yesterday or 2 days ago, when I was showing you debugging with GDB, and we were trying to figure out when something crashed, I would type in the term backtrace, and I would also, or it would actually just say call stack there, and you would see the different functions as to how the code went. That's where that's coming from, actually. So even if you don't remember, just bear with me as to what this is. Okay, so now going back to actually the proper version of this, which is actually recursive, let's kind of see what happens here when you do Fibonacci 5. So with Fibonacci 5, we actually go from left to right and we see the function called to Fibonacci 4. At that point, Fibonacci 5 stops and creates another function here in the call stack called Fibonacci 4. That has its own memory objects, and that has its own line of code that is basically Fibonacci's 3 and 2, which is going to create another object here for Fibonacci 3. And this gets paused. This function gets paused just like this one did, just like main did, when it sees the function call to Fibonacci 4. And this one when it sees the function call to Fibonacci 3. Now, how it switches around between that's CS326's level of stuff. Okay, you will talk about that in detail there. But for now, I'm just giving you a brief introduction into that to actually, this is all just to state a single point, which I could just tell you and spoil it, but I think it's better if I kind of lead up to it. So from there, Fibonacci 3 gets Fibonacci's 2 plus Fibonacci 1. However, we first run this one, so this stops and then goes down here, and then we go to Fibonacci 1. Fibonacci 1 has no recursive calls, because that one is, we already know that Fibonacci 1 in the if statement is just equal to 1. So then this finishes in the returns up here. So this gets removed from the stack. And again, removal is more of like the allocation. It's still there, but you can just override it and just ignore it. And so since we did this line of code, we still actually have to do the second call. We still got to do fib1. So we do another fib1 here. And then this code runs, does the fib1, finishes, because again, that one has no recursion. And then finally you do the addition of that. And then finally fib3 finishes. And then you go back up here. And this one was actually a fib3 plus fib2. Okay? And so this keeps going. So here's the thing. Each of these function calls, you know, they take memory. And more than just that they take memory, the bigger the Fibonacci number is there, the more calls that we're going to have sort of chained and on standby. And because each of those takes memory, this can be very expensive to run in your computer in terms of space. Because like if we have Fibonacci 20, at one point in time, we're potentially going to have a chain of 20 functions inside of the call stack just to get there. I can prove that to you actually with the GDB debugger. So my dog is just literally like, my hand is wet. She was licking it. It's annoying. Okay, now she left. Perfect. Let's go ahead and actually let's do it with the Fibonacci 11 since we have that one that's iterative. This one. Yeah, so that's line 35. So what I'm going to do is I'm going to recompile this with the -G flag. And then I'm going to do gdb a.out. And then I'm going to set a breakpoint at line 35. And now I'm going to run it. Now I'm in this line. If I type in here backtrace, I'm still in main, so that's okay. Let's go ahead and step into the function. So it checks the first two base cases. Neither of that is the case because it's 11. As you can see here, it says n equals 11. Here, n equals 11 right here. So it's going to go into the function call for fib10. As you can see there, it says fib10 now. And now let me just skip ahead right here until we get about to there, to 2, okay? So let's kind of see what I just did there. So with the 10, it skips these two lines, it gets here, gets the recursive call, then now we have 9, 8, 7, 6, 5, 4, 2. So now, let's go ahead and type in backtrace to see the call stack. Look at that. There's all of those functions are currently held in the call stack, and each of those takes memory. Now, it doesn't take a lot of memory because we don't have anything but one local variable, which is actually the parameter variable, the int n, but they still take memory. And so this could be a very expensive process. And no matter what, even if you have a function foo with no parameters and just a body that calls another function, just that is going to have a little bit of space in memory because it needs to be allocated. And because of that, if you have something that's just an infinite recursive call, every time that it does a recursive call, it's going to take memory away from your system as the call stack grows. Given enough time, which is actually pretty quick, your computer is going to run out of main memory and the whole system will crash. Or at least the operating system will crash will stop your program because it's like, yo, we're about to run out of memory and the whole computer will crash. So we got to cut our losses, you know, and so it just crashes you. But if it didn't, the whole computer would crash because it would run out of memory. And so you can see here the call stack. Again, this is actually smart because it's actually saying they're all in the same spot in memory, but again, they're not really. But you can see here, all of these functions are in the call stack. So yeah, and if once we start progressing here, when we get to fib1, it's still actually in the call stack still has even more things. Or sorry, not call stack, backtrace. And as we step out of them, because we are coming back, we start going up, partially up, right there. So backtrace, it's going back up into the chain, into the tree here. And so hopefully that proves to you that that is actually the case of how this is being built. So because of that, infinite recursive code is a bad idea because very quickly you're going to run out of space. Let's actually try that. Let's just make a very quick, here, we can do that by just commenting out the base cases with the Fibonacci sequence. And then now, that means it's going to go negative, okay? It's going to keep computing into the negative numbers because it's going to say like Fibonacci of 0, rather than it stopping there, it's going to say it's based off -1 and -2 spots. So let's see how quickly that crashes. That's pretty quick. It took in the millisecond range. So whereas an infinite for loop, you can run forever, no problem, no extra memory is being used unless you're allocating memory within the body of the for loop. With an infinite recursion, pretty quickly you're going to run out of memory and the thing will terminate. So that is why I'd say that even though, yes, you could have a recursive function without a base case, it's absolutely useless because you will run out of memory within less than a second. Okay? So, yeah. Also, because if you don't have your base cases, your thing will crash when it runs out of memory very quickly, you can see how this can be a great and really fun thing to try to debug. So, yeah. In fact, let's see how deep this goes before it crashes, how many calls it does. I've done this before. It's actually not that big of a number because the system stops you pretty quickly when it sees you're doing bad things. But we can do this by using GDB. So just run it. And now we get a segmentation fault. Cannot access memory at this address, which means it tried to put something in the call stack, which then it couldn't even access because it was beyond where the program's allowed to write or read. So we type in backtrace. You can see that it was actually only up to, well, pretty big actually. 174,000 recursive calls right here. This only says 20 because it's only showing the first 20. It says type return to continue. So if you type in return, you can see the rest of them. But the easiest way to see how many calls it did is because remember, every time you do a call, the number is increasing. And so we can see up here that the biggest number that we got was 174,066. Let's try to run it again and just see if it's the same number. Start from the beginning, yes. And then backtrace. And as you can see, it's pretty much the same number. Again, that is more than likely the system is only giving us part of the main memory. I do believe there's a limit. And so essentially it's just stopping us. So it's good that it stops us because otherwise we could literally use the entire memory of the computer. So yeah. Okay. So hopefully, this is all helping you to warn you that recursion is great, but things can go wrong very quickly, very easily. So you should be asking you if you're really understanding this, you should be asking yourself why we want to use recursion if it uses so much space, because it turns out that the iterative version of this code is not only faster, but it uses less space. So why use recursion in the first place? Well, the reason why is because sometimes as a programmer, I prefer to write code that is easier to write than it's more efficient to write, because I can always go back and change that code to turn it into an efficient version, or I can trust the compiler to do that, because it actually can do that. Not maybe in C++, but in Python. Python has a way of turning this into dynamic programming, which is a concept you'll learn later on, and it actually will save the answer to whatever a function call was on. So like it will save what Fibonacci 11 is, so that the next time it gets called, it doesn't have to undo the whole recursion to do it. It actually keeps track of it in some sort of array per se. And so it turns out that that it's actually pretty smart. It's a pretty smart thing to do to keep track of that, because then the next time it calls, you don't need to compute it again. So it's kind of like it's actually called memoization, which is no surprise sounds like memorization, because it remembers the answers to previous function calls. And so that allows us to still be able to write recursive code and still be very efficient. In fact, even more efficient than iterative code, because it wouldn't be able to do that with iterative code. So aside from those cool cases, I do agree with you that recursion can be counterproductive if excessively done. It should be only done in cases where the algorithm that you're trying to do just requires it without overly complicated and making the solution to a problem 10 times harder. Examples of that are actually very common when you get to 302. In 202, not quite. We're going to use it as a toy, and you'll be kind of annoyed, but that's kind of how it's going to be. So assignments, I think it's 10 and 11. I know we don't have that many number assignments, but I skipped some numbers, but assignments 10 and 11 are, I think, the ones that are recursion. There's part 1 and part 2. They're both due at the same time. They're basically one big assignment, but I split it into two. It's just doing a lot of little tiny recursive functions to do like very basic stuff, just to kind of get you warmed up into that recursive mindset, which does take some time to get adjusted to. When you get to 302, you will find a couple of algorithms that are like 50,000 times easier to write recursively than iteratively. Iteratively, again, meaning code with loops. Examples of those that I can tell you so you can look them up ahead of time if you're curious are one of the best sorting algorithms out there that is known as Quicksort. There is an iterative version of Quicksort that is known as Lampsort. Way complicated, way harder to do. If you told me like you gotta go teach these guys in 302 Lampsort or Quicksort, I would take Quicksort over like any day over Lampsort, because people will be just lost. Other algorithms are traversals and trees. When you learn about trees, that's also very useful. A lot of graphing algorithms are useful to do recursively, and in general, a lot of math-based stuff, because math people love writing things recursively. In fact, you will learn all about recurrence relations in 302, but you'll also learn about them in math classes, and they're great and really cool things. But again, this is the whole idea that math people love writing things in sort of recursive manner. Because of that, it's nice that we can easily convert them that way. And then, at least for prototyping purposes, it's very nice. I heard from the UCCSB computer science that it's easiest to code recursive in quantum computing. I'm not sure. Quantum computers, I am actually going to research them, because I do want to give a lecture in 2019 about that next week. So maybe I'll let you guys know next week about that. Why would that be the case? I don't know. So I can't. I don't know. Not sure. Where are you? Okay, so did they talk about that? Like, post a link to the paper that they were presenting about it, and then actually I could actually read that and maybe show it to my 2019 class. But I do have intentions of. I mean, like the quantum guy. Well, the qubits have multiple states, but maybe it's a little bit like memoization in a way, and maybe that's why it's better, possibly, because like maybe it's easier in the sense that like if you can write a function that does something with quantum computers, like if you got a function that can finally figure out how to compute this value, you know, and that function, you know how to do it, then yes, if you write your code in terms of those functions that you already have figured out how to do in quantum computing, then I can see how it would make sense. You know, that's the only thing that I can think of off the top of my head, but I'm not sure. Like I said, I actually had intentions of reading a little bit more about quantum computing to talk about it in my 219 class as the last topic. So maybe we shall revisit that next week once I'm actually more educated on quantum computing, and I'll Google that, because people who are in 219 should have already taken 202, so don't know about recursion, so I can actually bring that up. So also may be easier because it requires much energy to maintain or measure state, since they use the MRI for that. I don't know. Quantum computing is one of those things that is so exploratory right now that, because I mean, don't get me wrong, you get the articles that say like, we just figure out how to do this in quantum computing in a better way that we can do it in regular computing. But then you look at it in detail, and it turns out that the only reason it's better is because they're trying to do like RNG, and quantum computing is still so obscure that everything is basically RNG to us. So yes, they can do a random number generator better in quantum computing than regular computing. But I think that's just kind of cheating yourself out, and it's not really, we're not there yet. Hopefully we get there, you know, but not yet. Remember, for all the most complex ways you could solve. Yeah. And even so, like, you know, I mean, hopefully we get there someday. Let's just put it that way. But okay, coming back to this class, you know, you guys should say you're lucky. Imagine that we knew already quantum computing, and then you have to learn it in quantum computing now. The class would be like 50 times harder, you know, probably. I don't know what's going to happen then. It's be cool. But it's definitely going to be trickier for people to understand. I bet you that much. That does make me think about a point, though. Some places, before they teach you loops, they teach you recursion. And it turns out, studies of these people, they've done studies on people where they did that it actually makes it easier for them to understand recursion, but then they have a harder time grasping how loops work. So that's kind of interesting. So for example, the language scheme, the functional program, it's called functional programming. It's a different paradigm of programming. It has no loops in it. At least pure scheme doesn't have loops, and everything is done in terms of functions. And because of that, whenever you're trying to do something in a repetition, you use recursion for that. And so people who learn as their first programming language a scheme or functional programming in general, or variations of that, have a harder time than actually going into iterative code. And they have that same sort of struggle that people have when they go from iteration to recursion. Whether the struggle is worse or better, I can't remember, but I think they said it's just about kind of like around the same levels. But it's interesting, you know, it's interesting. Imagine that when you took 135, they hadn't told you about loops, and instead after they taught you functions, they taught you recursion as a way of doing loops. You know, and imagine how your life would be like. Would it be better? Would it be worse? Who knows? But now it's, you know, it's too late. We taught you the way of doing loops first and then recursion. Oh my god. So yeah. So anyways, back to this. For the last half an hour of the class, I'm going to show you this sort of tree structure of figuring out how to compute by hand a recursive function, which is a bit of a challenge, and it's good to know, because sometimes when you're, what's going to happen? You're going to code this thing, and then it's not going to work, and you got to debug it. And debugging recursive code can be very tricky. You can use that thing that I was using to kind of follow it along, but sometimes it's good to be able to do something on paper, good old paper. So let's do it with the Fibonacci, and then we might, if we have time, we could do a Bob Ross one. But the Bob Ross scares me because there's three things to the addition. So yeah, let's just stick with the Fibonacci for now, okay? So I'm not going to get too ambitious. I'm going to start with Fibonacci 5. So let's say we want to compute Fibonacci 5. Now, we can already ahead of time know what that is. You know, we could compute it from the beginning, and it would be super fast to do. You would just do 0 plus 1, 0, 1, 1, and then 2, and then 3. So I think this is going to be 3, actually. Maybe we should do Fibonacci. No. I get ambitious. Let me tell you what happened. Last time I taught 202, I did the Fibonacci, I think. And I started with like Fibonacci 8. And I spent like an hour doing this in class. And then at the end of the class, everyone was scared because they saw this massive tree that I'm going to write. And they were like, oh my God, are we going to do that in the test? Or something like that. And I don't want to scare you guys by putting such a big tree. It was cool. Don't get me wrong. I took a picture of it. And I still have that picture. But it was definitely a little bit too overkill for showing this method. But I do warn you, though. I will ask you to do this on the test. You know? I guarantee you. I love asking this question on the test. I asked the people on Discord that took my 202 before, and they'll tell you about it. I asked them with something that was heads and tails, which I'm probably gonna just use the same question but tweak it around a little bit because I love that question because that's a question that I got asked when I learned recursion, and it got embedded in my brain probably from trauma, but I did get it right to the point that now I must spread the trauma as a catharsis for myself. Okay, so this is one of the ways. This is how I do it, and this is how I was taught, and this is how I'm going to teach you of how to be able to compute something recursively by hand. Okay, so what I'm going to do is I'm solving Fibonacci, and I can look at the code, or I can look at this. Again, both are basically the same thing. You know, it's just an if statement in one of them, and the other one here is just a square. So I'm going to put both of them actually here, so that I have them for reference. Okay, so I have that. And then I have, where is my Fibonacci? This one, okay? Yeah, you guys should really ask on Discord to those. Ask the guy with the 2 asterisks. His name is like Maya or whatever. He's on Twitch sometime. Okay, so here we have them both. I'll put him like that, maybe. Okay? And so, all right, let's do it. So, we know that Fibonacci 5, and we have those here, actually. I kind of did them here ahead of time, because I thought that actually would be useful when we were doing this. So, we're also going to bring this down here. This is all preparation work, really, for what we're about to do here. And by the way, I'm gonna gloat now. Ben Cisneros was with me who's the guy who teaches 326 right now. He's still a PhD student, whereas I finished. But he took at the same time that I did that 202 class, and he also had that question that heads and tails. He got it wrong, and I got it right. And in fact, actually, there's only like 3 people that got it fully right in the class. Yeah, I think 3, or maybe 2. But yeah, so you can say like, hey, you got that wrong. So whenever he gives, if you take a class with him and he deducts points in your test, you should be like, well, you deducting points. I remember when you took 202, you got the heads and tail question wrong, and I bet you he's gonna get triggered. So who knows? Maybe he'll give you points back. So yeah. Okay. So Fibonacci 5. All right. Fibonacci 5 is going to be, well, yes, I was one of them, of course. I mean, I wouldn't be taunting about it if I got the question wrong. So, I mean, I'd be shameful at that point to say anything. So anyways, Fibonacci 5 can be represented as the additions of Fibonacci's 4 and Fibonacci 3, right? That's what the formula told us. So what we're going to do is we're going to build this, what is known as a tree. And this concept of a tree is going to get explored in detail in 302 to the point that you're going to be coding like 4 assignments on trees alone. But for now, a tree can be considered a data structure that has a parent and a child. And typically, if we have something that is known as a binary tree, it means it has 2 children. There are things like a ternary tree that has 3 children, but in here, we're going to do a binary tree. And why is this a binary tree? Because the Fibonacci sequence is based upon 2 values that you have to add together. That's why it's binary. However, Fibonacci would actually be a ternary tree because it has 3 values that we have. We had like the n minus 2, n minus 3, n minus 5. So that would be a ternary tree. So that's why I didn't want to go straight to that because yeah, that'd be a little bit more confusing if you've never seen the tree before, which you probably might have not unless you're a math person. So okay, so from there I'm gonna basically say that Fibonacci 4 or Fibonacci 5 is based on the additions of Fibonacci's 4 and 3. Okay, so I can put it represented like this. However, I still don't know what either of these answers are. And so now my tree is going to grow, and I'm going to split this here and say, let's actually do this side first. Let's do Fibonacci 3, because we can Lego it back in this. Well, yes, you do it in Math 351, but I don't know if you guys have all taken that, because a lot of the people are like, that in 202 might be like freshmen or sophomores who are just like their second semester at UNLV. They might have not taken the math classes yet, so that's why. The G and N minus 1 plus 1 is just a chain, right? There is no plus 1 anywhere. I don't know where you came up with the plus 1. Oh, you mean in general? That would be a chain. Yes, that would be a recurrence relation actually, and that would just be a function that basically adds up every single number backwards. So you still need a base case for it. If your base case is like 1, then that means that it would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Actually, no, it would be counting down. So your base case has to be like 20. So it goes 20, 19, 18, and so on. So yeah, that's recurrence relations. That's 302 stuff. You don't need to worry about that in 202. Just tell the people that they're learning in 302, and I'll teach it to them. Okay. So then Fibonacci 3 is going to be based on the answer of Fibonacci 2 and Fibonacci 1, which we already have because we have here. I'll even write it here. Fibonacci 1 and Fibonacci 0 are equal to 0 and 1. Okay, and so the tree stops here, because this one we know is equal to 0. Okay? Over here, however, 2 we don't know the answer to. So we have to do this in terms of the recursive call. So Fibonacci's 1 and Fibonacci's 0. Okay? Which those we do know that are equal to 1 and 0. Okay? So now, because this is 1 plus 0, it means that Fibonacci 2 is actually equal to just 1. And because now we have the left and the right, we can do this addition, and it tells us that Fibonacci 3 is actually equal to the addition of Fibonacci's 2, which is 1, plus Fibonacci. Oh, we put Fibonacci 1 and 0 there, but actually I made a mistake. This is actually 1 here, because that's 1 there. So, see that? Okay. So yeah. So essentially, Fibonacci 3 is going to be 2, which we already know, and we can even keep track of that here by writing it down so that we don't have to repeat it anymore, plus 1, which is going to be equal to 2. So now we have Fibonacci 3 solved. Okay? So now for the remainder of the tree, we have the left side, which is Fibonacci's 3 plus Fibonacci's 2. However, this is where you got to be smart. You already solved 3 and 2. That's actually equal to 2 plus 1. So then this is actually equal to 3. And then finally, 3 plus 2 is 5, which means that you solved that. However, if you still want to do the tree, then, you know, be my guest. You could just go ahead and copy this part over here. Try that again. Gotta shrink it down, because really the real tree, if you were to draw the entire tree of what this looks like, it actually would look like this. And then we still have one more little piece, which is up here. Let's shrink that. Come on. There we go. And here, let's put a little border so we don't get confused. Okay? And maybe here as well. But yeah, that is basically how you would draw the tree, the recursive tree. So this, you can consider this to be the recursive tree for Fibonacci's 5. Now let's go ahead and do Fibonacci 6. Okay? Fibonacci 6 is the answer of Fibonacci's 4 and Fibonacci's 5. We already have the answer to that. So we can go ahead and basically just take that. Of course, you can imagine doing this by paper. It can be a little bit painful. But that's why you want to keep track on the side what you've computed already. Which is, again, kind of like the whole Python's memoization thing. Because now, you already got this. There. And then you also have actually Fibonacci 4 already computed as well. Let me just make this tree a little bit wider. Like that. Fibonacci 4 is actually this chunk here. This thing is glitching out. It just inserts and like unselects it for some reason. Like that. I guess I make it a little smaller so it's the same size. So there you go. That is basically 5 plus 3. Which tells us 8, which is the next number. And so, yes, you will be making these trees on the exam. And a little bit trickier than this, actually. Because let's go ahead and say that there was even and odds involved, okay? So, let's actually, before we go there, like handwriting? Yes, like handwriting, you will do it. Yes. And so this will definitely be a considerable chunk of the exam, actually. Like 20 minutes worth of your exam time. So expect that. Yes, yes, yes. Scary stuff. Like I said, it's not easy. I mean, you know, Ben got it wrong. I got it right, but like most people got it wrong. And it's because it's not because it's hard. It's not hard. I mean, once you understand recursion, it's not hard. It's hard. It's tricky because it's a very high chance of making a mistake if you're not careful when you're doing this. Okay, very, very high chance of making a mistake. So you have to be very, very meticulous about this. So just to make sure that you don't screw up something. And I actually I did today right now. I had put a 0 here. I caught up on that. You know, I fixed it in the beginning. You know, rewind the video if you're watching on YouTube and you'll see that I fixed it. But if I hadn't, the whole thing would be messed up because the whole tree would be off by 1. And so, you know, you have to be very careful. You have to practice doing these trees. So maybe I'll let you do the Bob Ross. No, but I do want to do a ternary one. So what you can do is you can try this with a Fibonacci, but try it with a 7, you know, and forget about the ones you saw. Try it from scratch from a 7, and then practice that way. Because I do want to do the Bob Ross Nachi one. So let's go ahead and take that one next. So there it is. Okay, we're going to put that there. And so let's go ahead and compute it for, I think we can go for something like 8 without being too extremely ambitious, because it goes down quicker because it's -2. So it shouldn't be that big of a tree. At least that's what I'm hoping for. But let's try it. So B of 8. This is a ternary tree because there's 3 functions in there. Is 7 the answer? I don't know. Well, actually, no, it can't be. It has to be an even number. So it can't be. It can't be a 7. Or if you mean like we're doing on 7th, no, we'll do 8. We'll see what happens here. The question is if I have enough space in terms of width. So let me just start out by going really wide in the first layer. Okay, and so B of 8 is basically made up of B of 6 plus, and by the way, I could have a mixture of pluses and minuses. I never did that, but you can do that. B of 5, because 8 minus 3 is 5. And then B of 8 minus 5, which is 3. I kind of like how that's a mirror thing. It feels good. Oh yeah, this is not hard at all. This will be actually pretty small tree. Because already here we know that this is equal to 2. These two we don't know, but here, in fact, because we already know that this is equal to 2, I'm gonna actually move this a little bit, and then I'm going to put this really wide, and then just kind of put that here, and then we'll put a line here so we don't get confused. Okay, so that way I can put the B of 5 more like this way, so I have more space in general. Okay, like that. All right. So it doesn't matter which one we do next, if we do the 6 or the 5. However, I recommend that you do the smaller number, because then you can use that for the rest of it, and it's just less chance of errors that way. Or you want to catch your errors earlier in the process. So this one is going to be made up of 3 pieces as well. It's going to be basically made up of B of 3 because it's 5 minus 2, B of 2 because it's 5 minus 3, and then B of 0 because it's okay. Yeah, I was just about to say this could have gone wrong, but we have a case for that. Never mind. The before. Yeah. Okay. Cool. So B of 0 is 2, B of 2 is 4, and B of 3 is 2. So the answer to this is basically 2 plus 4 plus 2. So that is 8. So that is basically what B of 5 is equal to. Right there. On the other hand, we have B of 6 here. B of 6 is made up of B of 4, B of 3. Oh, that 3 doesn't look right. Try it again. And B of 1. Okay. All of these are given to us, so that's pretty nice. 4 is going to be 4 plus 3, which is 2, plus 1, which is 2. This is also equal to 8. Finally, B of 8 is equal to 8 plus 8 plus 2, which is 18. And there you go. We have now solved B of 8. Let's suppose we try to solve B of 9 now. And you might be thinking, oh, well, the previous tree will be helpful. Not in this case. I mean, it might, partially, but not entirely. Because that B of 8 is actually not even going to be used to compute B of 9 because of the way this is set up. So now that we solved this tree, let me shrink it down a little bit. Actually, no, I kind of like it where it is. Let me just copy this beneath. Okay, so B of 9 is going to be made up of 3 things again. And those 3 things are going to be B of 7, B of 6, sorry, yeah, B of 6, and then B of 4. B of 4 is equal to 4. B of 6 and B of 7, do we have either of those here? We have B of 6, so at least that part is going to be useful. So hey, that's kind of nice. Now the only one that we're really gonna have to compute is b of 7. So because I don't have enough space there, I'm gonna do it down here. Like that. So even though the tree, it would be at that layer, this is okay to do. So in fact, even more than that, I'm gonna kind of, damn it. B of 7. I'm gonna put it down here like that, just so I have more space, okay? Can you explain that again, please? Which part? Which part? Oh, how do you determine that how many leaves it's made of? Oh, it's based on the number of recursive calls that you have to do in a given function. So for example, with Fibonacci, if we look at the math of Fibonacci, there's 2 of them. F of n is related to 2 recursive calls, f of n minus 1 and f of n minus 2. On the other hand, Bob Ross is made up of 2 function calls, 3 function calls, sorry. You have n minus 2, n minus 3, and n minus 5. So because it has 3 function calls, then your tree is going to have 3 branches. So the number of branches is equivalent to the number of function calls that you have in your recursive function. And those function calls have to be all required. Because you might have a situation like this. You might have a situation where you have a specific, where you might have like, if a is greater than 5, or if n is greater than 5, do this recursive call. Otherwise, do that recursive call. In that case, they're not being run in parallel, per se. One of them is happening, and then the other one is happening. Or actually, sorry, one is happening or the other one, but they're not both happening at any given time. In that case, the tree would actually only have 1 branch. It would be like a unary tree. So that would be like the example that that was given earlier with g of n is equal to g of n minus 1 plus 1. That actually would be a unary tree. We could do that one too. So maybe I'll write that one down to do after we finish this one. So g of n is equal to g of n minus 1 plus 1. So that would be a version that this would be a unary tree because there's only 1 recursive call. But you could also have a situation again, like you have something like if n is greater than 10, do something like, this is like foo int n. If n is greater than 10, do like foo n minus 2. If n is less than 10 or equal to 10, then do f of n minus 1. You could have a situation like this. That is not a binary tree because, actually, well, it is now because of that. Actually, no, it would never happen, but I don't need to do this like this. I overcomplicated that. I could just do else here. And that is not a binary tree like this because it's going to run 1 recursive call or the other one. In this scenario, one child, so unary tree, okay? In the other scenario, this just means that it's always going to be 3 recursive calls. It's never going to be a situation where it's 2 or 1, it's going to be 3. And then with Fibonacci, again, it's always going to be 2, okay? So, good, cool. It's a good question to ask, actually. So, yes. This, by the way, is actually an interesting recursive call to do. So, let's go ahead and finish this up. So, we got B7 is going to be made up of B5 plus B, 3. So, that would be 4. And then minus 5 would be plus B2. So, this one we know is 4 and 4 based on these guys here. And then B5 we don't know, but I think we already done it. Yes, we did. Perfect. Awesome. That means we can wrap this up very quickly here. Move this down a little bit. And then let's go ahead and put that here. So that's our B5 right there. So we don't need this anymore. And then we might have to shrink it just a little bit so it fits in here. Right there. Okay. So the addition that we have to do here is 8 plus 4. Here, that's a 4. That looks like a 9. It's just 8 plus 4 plus 4, which is 16. And so now we have 16 plus 8 plus 4. So that is going to be 28. Let's confirm that with our program really fast, since we coded that. So 9 here. And this will come in useful to you. Oh, with when you're doing the exam, because you have access to an IDE. So you could code the solution to test it, just to make sure that you got the right answer out. But I am expecting you to draw the tree. Oh, I forgot I had these commented out. So I got a 28. So yeah, we got the right answer. So cool. So you can code it to test yourself, but I still expect you to draw the tree to make sure that you understand what is happening. And yes, I am okay with you doing it like squiggled up like that because it doesn't fit in one line. You know, it looks nice like this. Like this one looks pretty, you know. This looks great and all, but of course, you know, the trees can get really wide. On the test, will you make us do the entire tree? Yes. You can yes, you're right. You can refer to previous branches. So like how the fifth tree here that I had down here, how this fifth tree here, I was basically using this tree here. I'll just copy and paste it. You can indeed refer to it. So you can just write fifth tree and then put the number and then you have it over here. So yes, you can you can indeed just put you can refer to other parts of the tree that you already computed, okay? But yeah, just scan the answer, yes. Or if you're feeling bold, you can use Paint and try doing it in Paint. It's not that bad, actually. But yes, you can also, there is an app that you can use to take a picture of a paper and immediately send it to, well, I mean, what is the purpose of the app? I can't remember. There's an app that my 302 students were using. Ask on the Discord, and they'll tell you, because they went through this process of like drawing like a million pictures. Because in 302 it's all about like being Bob Ross here. You're really just drawing all day in that class. So I might have been, but I don't know what they were using it for. I can't remember now. Like, well, I guess it was converting a picture to a PDF. I don't know. All I'm thinking is the easy way to do it is just take a picture, email it to yourself, and then upload that. But maybe the process here was so that they would interface with the computer so they could send it quicker without the email section of it. I'm not sure. So, yeah. But yeah, it actually would be a good idea to get this system that you're going to use set up so that when the test time comes, you're not trying to figure out an app name or something. So test it out, you know, try drawing something, go Bob Ross and me, draw something, and then try to send it to your computer as if you were going to upload it to Canvas. And then once you got that system worked out smoothly, have a redundant system up, like using Microsoft Paint or a tablet, which is obviously the ideal scenario. But yes, that will be something that you will have to kind of set up. So anyways, for the last 5 minutes here, let's go ahead and do a Unary tree solution of this, okay? We do need a base case for this. But even without it, let's just kind of draw this for a little bit. So let's just say we're doing this on G of 5. So G of 5 is going to be essentially G of 4 plus 1. So whatever G of 4 is, plus 1, okay? G of 3, that is of course based off of what G of 3 is, plus 1, which of course is based off what G of 2 is, plus 1, and then based off G of 1 plus 1. But yet again, we need a base case to this. So let's just say that G of 1 or G of 0 is equal to 0. Let's just say that's our base case. So G of 0 is actually equal to 0 plus 1, which means that G of 0 is equal to 1. Or sorry. G of 0 is actually equal to 0. So because of that, we bring it up and say that G of 1, or sorry, I think I might have skipped ahead. G of 0 is equal to 0 here, like that. So technically this is plus 1 here. So then this would basically mean that G of 1 is equal to 1 because it's 0 plus 1. And then G of 2 is actually equal to 2. And then G of 3 is equal to 3. G of 4 is equal to 4. And then G of 5 is equal to just 5. So, yep. Hopefully we didn't mess up the plus ones. But essentially, that would be a very easy version, which I promise you, you're not going to get a unary tree in a test. You're going to get a binary or a ternary tree. So yeah, but still, it's a good example of a unary tree version where there's only one recursive call. So yeah. So for the given trees, we'll be given both the base and recursive cases. Yes, you will either be giving it in a math format, or more than likely, since this is a computer science course, you're not going to get the math format. You're going to get the recursive format like this. You're going to get something probably like this. And then it will be your job to figure it out. Because, I mean, you know, I'll let the people in the Math 351 give you that one, the blue box. I care more about you understanding how to figure out this code, because that's what you might want to debug someday. So that's the one that you're going to get. Obviously not Fibonacci, because we did that. But my own version of the heads and tails problem. And again, it might be a good idea when you're doing the assignments for the recursion to try and doing them by hand. That's going to be good practice. And that's actually one of the ways that you'll figure out if you actually coded it right. So it'll be good practice like that. But that's pretty much all there's to recursion. I suggest that you look at the book, I suppose, because they have an example with factorial. And factorial also lends itself very nicely to recursion. And they also talk about the idea of recursive algorithms, which is kind of what I was talking about. Oh, here they got the word recursive function. They show you examples of call stack. Direct and indirect recursion is what they call that circular recursion, where like foo calls bar and bar calls foo. They call that indirect recursion. And then direct recursion is more of what we're doing, where you're actually calling yourself. Then they have us thing about infinite recursion. And then they have this kind of nice sort of write-up about how to approach solving a problem recursively. You can try reading that and see if it helps you to better understand recursion. If not, I guarantee you that you type in recursion on Google and you get a billion different videos with a billion different examples. Hopefully, you know, that amongst with you practicing kind of really gets you to understand. Because I mean, recursion is one of those things that, yeah, it makes sense, base case and recursive case. But, you know, there might be other ways that somebody writes this. So here, I'll close the lecture by putting another scenario that could happen here, okay? So I could rewrite this Fibonacci sequence into one other way. And I'm going to do that really fast. This, of course, looks really nice because it's very clear and obvious to see the base cases and the recursive cases, right? We can see that these are the base cases. And this is the recursive case. However, another way to write this function, and it will do the same thing, would be to do something like if, so, well here, let's write the full function. So int fib int n, okay? Oh no. See, it's as soon as the time hits, it's just like a clock, you know, like an alarm clock. So yeah, we're gonna say if n is greater than 1, and then go ahead and put the recursive case in there like that. Else if n is equal to 1, return 1. Actually, here, just to hide the word return many times, we're gonna say int n is equal to 0. Or sorry, not n, just another value. Let's call it v. Int v is equal to 0. And so now instead of saying return here, we're going to say v equals that. Otherwise, v equals, I think, 1. And then and here we're just going to say return v. Okay? This piece of code will do the exact same thing as the one above it. And I'm not trying to be tricky with this code. It's just betterly written, frankly, because writing multiple return statements in a function is like writing break statements in a for loop. it's not looked upon nicely. With the exception, frankly, of recursion, I'd say it's okay. But some people might not even want to do it in recursion. So they might write it like this. And this does the exact same code. You don't need the third if statement that says like if n is equal to 0, because that's going to be the only other scenario that you would run into here. So because of that, identifying based on recursive cases is not as trivial as it is with the example that I gave you with the Fibonacci. So yes, that is going to be a trick to I mean, I think in the one that I give you for the test, it's kind of obvious which ones are which, but I'm saying in general, it's not always as trivial. So yes. The singular people. Yes. So yeah, it's a little bit challenging sometimes, okay? So that's kind of what I would just want to close it off with. So when you're doing the assignments, I think I just tell you to solve a problem recursively. And so you typically want to, when you're learning recursion, just stick to making things very clear, but be aware that you will run into code that is recursive code. And the easiest way to see it is because you will see the function name. That's going to be your sign that it's recursive code. You're going to see the same function name in the body as here in the definition. But again, it's going to be iffy. Okay? So, yep, that's just, I just wanted to leave you from that excited version, like, yeah, recursion, to like, oh no, this might be harder if I can't really separate base and recursive cases. So, yes. With that, the weekend has arrived. I hope you guys have a good weekend. My recommendation for you is that this is the last weekend before the exam. So I believe I already published, or if not, the recursive homeworks will be published in 2 minutes at 7. But I also published the linked list homework and every remainder homework for the semester. So if you want to get them done this weekend, you can. But at the very least, make sure you get everything up to the recursion done, so that next week can be focused more on learning the last topic, which is the linked list and stacks inclusive if you have time, and also preparing for the exam. Don't procrastinate that, because otherwise next week will be worse than hell. So yes, we just had some recursion right there. You want to see what recursion is like? That is recursion right there. So yes, trippy. So yeah, fun lecture today. Recursion is definitely an interesting topic. It's definitely it's kind of a refresher now that we're done with learning programming, and it's more about learning concepts, because it's not templates and operator overloading and this and that, pointers and whatnot. Now it's just like concepts, and it's a little bit refreshing to just kind of have a relaxing day. Are you gonna give us a study guide? I'll give you tips like last time, but study guide is hard because I'll tell you what the topics are, but like it's not like a class where I'm like, you should memorize this term or that term. Like, hey guys, remember what a base case is and what a recursive case is. Yeah, but that's not really gonna help you if you don't really know how they function and whatnot. So that's why it's kind of difficult to give a study guide in a computer science course. That's not 219 is perfect for study guides, because like that is the here's the book kind of thing, and there's like a billion different definitions in here and a billion different things that you should know. That one is like great for study guides, but a programming course is just difficult for a study guide. I don't know how to achieve one of those. Maybe I should make it an extra credit to create a study guide for future semesters, but even so, like that'd be so challenging to figure out if it's a good or bad study guide, because we wouldn't know until the next time. I am teaching 202 in the fall, so yeah. How about that? In addition to making the notes as extra credit, let's make that be a potential extra credit. Make a study guide if you want, and you can work with somebody else on this if you feel like it. But make a study guide that you think would be useful for students in the future. See if you can come up with something. I don't know if it's doable, but try it. And if you do, then you can get some extra credit. Also, don't forget there is the bug detection for the app. That is also another way to get extra credit, along with the Twitch points. So yeah, we'll try that. Is the exam going to be everything after the midterm? Yes, but there might be things from the first part of the class, not intentionally, but like it just there might be pointers involved, because when we talk about linked lists, there's pointers involved. So I'm not going to intentionally be like asking you like define operator overloading kind of thing, but some of the stuff will just inevitably appear because it's part of the language. It's just like it's unavoidable. Like there's going to be variables, right? And that's a 135 thing. So it's inevitable. Do you know when our midterm grades will be out? I don't know. I thought they were already out. I'll talk to the TA about that. He should be on point with the grading. So I do know for 219, like the grades were done like 3 days after the midterm. So I'll check with Puyan about that. Yes, there will be partial credit if you get like say you get the let's say you get the recursion wrong, but it's almost right. You know, you just screwed up one of the additions or something. Then you're gonna get most points. Similarly, if you mess up something in the test, then you should get partial credit. And but now I'm worried about the midterm. You guys haven't? Oh gosh, because the whole point of giving you the midterm at the middle is that you get the grade before the drop date. But I mean, I guess I know you kind of know how you did. Most people kind of know. You know, most of the time it's like you have a range of numbers that you think how you did. But I'll talk to the TA about that. How many assignments have we had? Like 6, maybe 7. I'll talk to him. Yeah, I'll talk to him. That's not good. All right. I'll write to him actually right now once I hang up. So, well, I guess this weekend's gonna be very interesting because he's gonna be doing all this. So, yep. Thanks for letting me know about that. Cool. Anything else? Where did the dog go? The dog was here and then she left again. Okay, that's good. Padme comes and Padme goes at her desire. Great. Well then, get the homework done, but also try to enjoy the weekend and stay safe. We do have 2 weeks before the semester starts, like the real semester, like the regular semester. So enjoy the weekend and enjoy the rest of your summer, I suppose. Yes, but before the grades are due, because otherwise I can't change your grade after that. I mean, I can, but it's like a complicated process that it covers, like the chair's approval and stuff. So the deadline for the notes and all those things will be like 1:35, which is like that weekend by the Sunday, because then I can turn in the grades on Monday, because they're due by Tuesday at like 1 p.m. And I don't want to wait until Tuesday because, you know, I don't want to have problems if I accidentally screw something up and I need time to change it. So, you know. Yes, you can work on the study guide or the notes with or I guess the study guide or the notes with a partner. Yes, I haven't done it in the past before, where 2 people combine forces to create one of the ones that you see online for 202, like on the on Canvas, was created by 2 people who work together, and that's okay. I answered that already. So it's going to be focused on the latter parts, but because of the nature of programming, some things may appear from the first. And I think the biggest one being the pointer stuff, because linked list is a lot of pointers involved. So it's not like I'm going to intentionally ask you questions on stuff that was covered in the first part of the test. Like I'm not going to ask you like, you know, inheritance, like what is the difference between public and protected? You know, that's not going to come back. But, you know, there might be some code where the word private or protected isn't the code that you're looking at. So by that nature, you should probably know it. Virtuals are going to be coming back, right? Because virtuals were, I think, after the test. So because of virtuals, there might be some inheritance involved. And so that you can see the whole, you know, issue that we solved with when we had inheritance and virtuals, and, you know, like how it was calling the wrong function because of the compile time binding. So inheritance may appear in the test because of that, not because I'm asking you about inheritance in specific. When are you posting the grade for exam 1? Like I said, I thought the TA had to regrade it, so I will talk to him to make sure that he gets it done before the end of the weekend. I'll just give him that as the deadline. I'll tell him to grade test 1 before Sunday, and then to at least grade like 1 or 2 assignments, you know, because he's gotta catch up. Otherwise, like he himself is gonna screw himself over because, you know, he's got to turn in the grades to me before Sunday next week. So, yeah. So I'll make sure he gets things done. Cool. All right, then. I shall see you guys on Monday then. Have a good weekend. All right? Yes, you are getting the Inception assignment. You are indeed. So have fun with that. Cool. Bye, guys. And by the way, ask me questions on Discord. So I'll be around. Like, I'm going to go eat now, but like I'll be around to answer questions. So, yeah. Padme wanted to say bye. Hey, Padme. So, have a good weekend.